Hello and welcome to High Voltage Engineering. I will be continuing with our module 2 where we are talking about generation of high voltage and currents. Now in this module, it is the third part of this module where we are talking about the generation of direct or DC voltages. So we have covered a lot where we have covered different types of generation with rectifiers and voltage multipliers and voltage doublers. Now we have also seen the calculations of voltage drops for the voltage multiplier circuit. Now we'll be continuing, we'll see the regulation of voltage multipliers. Okay, so we'll talk about voltage drop on load and regulation. Now first we have to understand what is regulation. The change of average voltage across the load from no load theoretical value expressed as the percentage of no load voltage is called regulation. That means what? That we have a theoretical no load voltage and you have a voltage that is obtained when the element is loaded. Now the change of voltage from the no load to load as a percentage of no load voltage is called the regulation. That means, for example, let's say a device has an output voltage of 100. So when the device is loaded or the load is connected to a device, the voltage across the load drops to 90. So our percentage regulation will be 100 minus 90 divided by 100. So that will be 10%. Okay. The change in voltage, that is the voltage drop delta V, is caused due to the ripple small delta V. And the capacitors not getting charged to the full voltage Vm when they are supplying the load I1. So this voltage drop is actually due to the ripple voltage as well as the voltage drop in the capacitor. Okay, so the voltage drop under load condition delta V is found by assuming that all the capacitors are equal to the same value, that is C. It is seen from the analysis of a ripple that all the capacitors are not charged to Vmax, which we have seen in the previous class. The capacitor given by the C2n, that it is the even number of capacitor is charged to 2 Vmax minus N I1 divided by Fc only instead of 2 Vmax. So we are not getting 2 Vmax rather than value lesser than the 2 Vmax because the charge given through 2n minus 1, that is that one capacitor just before that, is one cycle equal to a drop of voltage of N I1 by Fc. This is because in each stage the loss of charge equal to the voltage drop of I1 by Fc to the load at every stage. So you can see that at every stage there is a voltage drop of I1 by Fc. So when we go to 2n, we have an voltage drop due to 2n when we have the voltage drop of the capacitor C2n, it is affected by the capacitor voltage drop of C2n minus 1. So in a similar manner, the capacitor C2n minus 2 is charged to only 2 Vmax minus N I1 Fc minus N I1 Fc minus N minus 1 I1 Fc. Since the reduction of voltage at this stage is further equal to N I1 divided by Fc at the capacitor 2n minus 1. So you can see gradually the capacitor value, the voltage drop across the capacitor value decreases. Okay, thus if the voltage drop at each capacitor 2n minus 2 etc. to C2 is designated as delta V2n, delta V2n minus 2 to delta V2, the total drop of the voltage will be calculated as follows. So you have in the right hand side we have the set of all the voltage drops of delta V2n to delta V2. Now if you sum up all those voltages, you will have an expression given on the right hand side, okay, which can be which can be calculated and made equal to I1 by Fc multiplied by the summation of 2n square from n equal to 1 to n minus summation of n, where n is equal to 1 to n. Okay, so which is at the end, which you have is I1 by Fc 2n cube by 3 plus n square by 2 minus n minus 6. So this is the total delta V, or the change in voltage from no load to a full load. This is given as the, now if you make that this in as a percentage of the no load, you will have the regulation. Okay. So it is seen from the previous equation that most of the voltage drop at the lowest stage of the capacitor, that is C1, C2, C3, C4. Hence it is advantageous to increase their values to be proportional to the stage number counted from the top. In other words, C1, C2 may be chosen as NC, C3, C4 as n minus 1 C. So what happens is that we have seen that the voltage drop across the capacitor that is close to the source have a higher voltage drop rather than the capacitor that are far away from the source. That means, so we can increase the value of this capacitance in series so that this voltage drop can be obtained in a uniform manner. So for a large values of n, that is more than 5, n square by 2 and n by 6 terms in 6.3, that is the previous equation. This equation given at the bottom on the right hand side, this equation, okay, will become small compared to 2/3 n cube and can be neglected. Then the optimum number of stages for the minimum voltage drop can be expressed as, so the number of optimum stages will be given by root over Vmax by Vmax Fc divided by I, where I is a load current. Thus, for a multiplier or a cascade circuit with a frequency of 50 Hz, capacitor of 1 microfarad, Vmax of 100 kilovolt and I as 5 milliamperes, the number of stages would be 10. Okay. Now on the right hand side you can have a one phase 2 pulse voltage multiplier circuit. So this is an example of a single phase and 2 pulse voltage multiplier circuit. Now a few points on the voltage drop on load and regulation. Regulation can be improved by increasing the frequency, but an upper limit is set by the high voltage appearing across the inductances and the high capacitor current which are considerable. So regulation can be improved with the frequency, which we have seen here, as the regulation is proportional to frequency. See in the previous so when we have the regulation has the frequency element here. Okay, so frequency can be increased to reduce the regulation. So delta V is proportional to 1 by F. So increase in frequency you can reduce the regulation, but what happens is that if you increase the frequency, the impedance suffered by the inductor, that is 2 pi f L, that will also increase. Okay, so a high voltage will appear across the inductor. Again, a high capacitor current will also be present if we increase the frequency. So at present, the Cockcroft-Walton type voltage multiplier are available using selenium rectifiers and AC supply frequencies of 500 to 1000 Hz of output voltage of more than 1 million volt and load current of 30 milliamperes. So in the present and present day Cockcroft-Fulton type of voltage multipliers are available. They use selenium rectifiers with a supply frequency of 500 to 1000 Hz, and it can create a voltage more than a 1 million volt, but with a load current of 30 milliamperes. The single pulse voltage multiplier has only one rectified wave or pulse per cycle. So in the previously which we have talked about the single pulse, one phase 2 pulse voltage multiplier. Now we have talked, if we talk about the single pulse voltage multiplier, it has only one rectified wave or pulse per cycle. Hence, since it is at one rectified wave, we have a ripple content is high. In order to reduce the ripple as well as the regulation and to improve the efficiency and power output, 2 or more pulse units per cycle are preferred. Single or 3-phase bridge is used as a basic rectifier or stage, and the multiplier circuit is built in same manner as that of the Cockcroft-Fulton multiplier. Now we will talk about the single phase 2 pulse cascade multiplier. The basic voltage doubler circuit consists of this rectifiers D1, D2 and capacitor C1, C2, and is replaced by a bridge circuit D1, D2, D1 dash and D2 dash with an extra capacitor C1 dash. The center tap of the supply transformer is connected to a junction of the rectifier D1 and D2. The arrangement is simply an addition to another voltage doubler circuit D1 dash, D2 dash, C1 dash and C2 dash along the transformer H1, H2 for a negative cycle rectification. Multiplier circuit is built for both positive and negative cycle rectification, and the arrangement is called symmetrical cascade unit. So we have seen the symmetrical cascade unit. Okay, this is this one phase 2 pulse voltage multiplier. Okay, you follow this diagram. Okay, the multiplier circuit is built for both positive and negative cycle of rectification, and the arrangement is called single cascade unit. The ripple for this arrangement is given as Ni divided by 2Fc as against to N into N plus 1 I 2F divided by 2Fc with all capacitors of the value equal to C, with a regulation of Ni divided by 3Fc multiplied by N square by 2 plus 1. So this is an expression, just you have to keep in mind the values that are given. This is a basic description of the single phase 2 pulse cascade multiplier. So you have a single phase 2 pulse cascade multiplier which is shown in the figure on the right hand side. This is the single phase 2 pulse cascade multiplier. So we have the extra rectifiers of D1 dash and D2 dash, okay, connected to and we have a capacitor in between every pair, okay, as you can see in the diagram. Now we talk about the 6-phase 6 pulse arrangement shown in the diagram on the right hand side. The 3-phase 6 pulse arrangement is a 3-phase bridge, or it's called the Gratz circuit, cascaded into multiple circuit. 2 more multiplier units for the other 2 phases of the 3-phase supply are connected in parallel to build this circuit. So you have parallelly you will have 2 more phases, similar phases that are used for the 3 phases. The ripple is now will be reduced, which since we have multiple phases, the ripple will be reduced to Ni divided by 6 Fc, and the regulation will be reduced to Ni divided by 3 Fc into N square by 6 minus N by 4 plus 1/3. The 2 pulse circuit requires double the number of diodes and 1.5 times of the capacitor required for the single pulse circuit. The 6 pulse circuit requires twice the number of diodes and capacitors used in the single circuit and as such the cost increases. So but still, if we use 3 single phase circuit, it will be much more cheaper if you use a single 3-phase circuit. Okay. But the regulation and the ripple are very much reduced, and the requirement is needed in the specification of DC test sources are easily met with a much smaller rating for the capacitor. So since we have a lesser amount of ripple for the 3 phases, we need a smaller capacitor to smoothen out the wave. So that is one more advantage. For the large current required for pollution testing can be obtained only with 3-phase 6-pulse arrangement. So again, the 3-phase 6-pulse can give you a larger amount of current. So you have 3 advantages here. That is, the ripples are lesser, so you can have a lesser rating of capacitor, and you can have a better amount of current if required. Okay, so this is the end of this lecture. I'll be continuing with the next lecture in the next class. Thank you.